what that position vector is. Ready? So that other differential equation is going to be this, and we're going to have to carry out the integration on this now from the initial position to the final position, and we're going to place our velocity vector in there that I'm going to go ahead and use the math angle bracket notation. So we have v naught cosine theta comma minus gt plus v naught sine theta, right? That has all of it, I believe. And then we have to integrate that over time. Okay, and we're integrating over time again from 0 to t. Right? Did I screw up anywhere?
The top limit, it's not a vector.
Yeah. Thank you. Boy, I would have gotten a point off on that problem, wouldn't I? Okay. Right. Okay. I'll get a little picky with you on time. I mean, you guys, I want you to pick on me, but I'll pick on you too, okay? So try to be consistent on this kind of stuff. So what we're going to get coming out of the integration over here then is we're going to get this change in position now. Change in the position vectors, which is going to be equal to then the integration we obtained from this side. So let's come over there. Now, I'll show you a little word of caution when you're doing your work on pencil and paper. So integrating this x-directed term, we're going to, over time, we're going to have v naught cosine theta times t. Be real careful that it's clear that that t is not inside that cosine argument, cosine function. And sometimes people like to do that just to be safe, okay? Don't tuck it right up next to your theta, okay? So we did that guy. Now we come over here and we integrate this one. Oh, I might as well keep it in the vector notation here. And so we're going to get a minus gt squared over 2 plus, again, a v naught sine theta this time times t. And that takes care of it on that side. And then the initial position kicks over to the other side, and we obtain the final position vector. Now, what was that initial position? It was made up of the x naught, y naught, which is back over on the our board over here. You kick those over to the other side, and they become additive to the I and the j terms there. So we get the theory worked out here. So we end up with, I'm going to go ahead and use ij notation now. So I'm going to pick up a v naught cosine theta times t plus x naught I hat, and then plus a minus gt squared over 2 plus v naught sine theta times t plus y naught j hat. So there is the position vector in general. Feel good?
Yeah, as long as we're in a vacuum.
As long as we're in a vacuum. This works reasonably well.
It'll work.
Yeah, it works for engineering. Engineering isn't quite as precise sometimes. It depends on the kind of problem you're up to or dealing with.
Yes, I've already started running this stuff involving air resistance.
Yes, yes. And we did a problem last session, I believe, where we had the oil bath. Our oceans and our atmosphere are considered to be fluids. Okay? It's just that the atmosphere happens to be more of a compressible fluid than the water in the oceans and the lakes and so forth. And that field of study is fascinating, and the mathematics gets pretty horrendous. Partial differential equations, because there's so many variables involved. When you add thermal input to that fluid, and then you also put it into a rotating earth, you get the thermal effects, heating the molecules, causing motion in one direction, and then you got the earth rotating, which puts the ocean currents into motion, and then you get the gases, the compressible fluids in the atmosphere starting to move across that liquid surface, and that creates the wave action and the weather patterns that we experience, which to this day are still not very accurate in the predicting, are they? Okay. Sometimes they're fairly accurate. Okay, well, back to this. So here's a position vector. Now, we all know that the path is a parabola, because you've believed the story that's been told to you since you were a kid, started taking math and science. How can you use that position equation to actually show someone that indeed the path is a parabola? What can you do with this vector equation of the position at any location to demonstrate that indeed the path is a parabola?
I think you could turn it into a parametric equation and then solve for the t variable and then set y as a function of x.
Sounds like a good idea to eliminate time, right? And because the question I was posing was, how can you confirm that this is a parabola? And parabola, the equation would involve x and y, not time. And that sounds perfectly reasonable to try that. So let's see. This is x right here, isn't it? Isn't that part of this thing x? And this part over here is indeed y. So we could take this equation for x and solve it for t. Looks like that's simplest. And then stuff that expression for t into that thing. Okay? Let's do it. You guys can go ahead and start working on your paper. I'll just go ahead and write it up here, and I'll say it out loud as I go. But see if you can just crank that out, that substitution. Solve this x equals this for t. Take that expression and stuff it in over there. And should I try to do it up here in that little bit of space? I'll try it. See if it comes across. So I took the expression for x being equal to this part of our position equation, and I solved it for t, and I substituted that into this equation for y. Minus g over 2 times the t squared term plus v naught sine theta times the t term plus the initial y position. We can clean this up a little bit by eliminating the v naught in the second expression, and we end up with y equals minus g over 2 x minus x naught. You know what I'm going to do? I'm going to tidy this up a little more. Minus g over 2 v naught squared cosine squared theta times x minus x naught quantity squared plus tangent of theta times x minus x naught plus y naught. Did I have that right? So it's a little quick two-step calculation there to show someone that this is of the form y equals some ax squared plus bx plus c, a quadratic function whose shape graphically is a parabola. Right? Notice this initial term out front here involves the g reading and these squared values down below here, so this leading term is less than 0, isn't it? Times x minus x naught squared, which means it's what shape of a parabola?
Concave down.
Concave downward, concave down parabola, always. Always a concave down parabola. Okay? All right.
What's P?
Where?
In the second part?
Here?
Oh, tangent, okay.
Yeah. We were able to eliminate the v naughts and turn the sine over cosine to tangent. Good. It's pretty slick. So most textbooks don't show this right here, but that sort of confirms it to us. Now, oftentimes, the projectile happens to be at the origin, doesn't it? So if x naught equals y naught equals 0, positioned at the origin, then your flight path is going to be simply minus g over your 2 v naught squared cosine squared theta x squared plus tan theta x. Which is a simpler quadratic expression that happens to be factorable. Happens to be factorable. So you could factor an x out of that. If I did that right. And why is that form useful?
Find out where it lands.
Find out where it lands and where it started. You can see the common factor here, x, and so that term being 0 means that your flight path, yeah, actually this is showing up pretty well on the graphics there, so I can go ahead and squeeze it in down here. I don't know if you can see it or not. And they've got a camera up there also, so you guys can look at what's going on. Here's your flight path, and so here's your x equals 0 factor. And then if you set this other term equal to 0, this point right here then has to be where this other binomial term equals 0. Right? So let me erase. Any questions on the theory so far? Because I want to add that little calculation in up here, but I don't have enough room to put it down there. Are you with me? Pretty straightforward so far, right? Okay. Oh, I'm going to have to make sure I erase this stuff fairly quickly. I brought a water bottle to try that on here. See if this works. Yes. Okay, so what I want to do is take that other binomial there and set that equal to 0 and solve that for x. So notice what you get coming out of that. It looks like we're going to get x equals 2 v naught squared cosine squared theta tangent of theta divided by g. Is that right? And then notice that tangent is sine over cosine, so we eliminate one of those cosine terms. So we get V naught squared over G times 2. I'm going to change the order of those terms. Sine theta, cosine theta. And there's a trig identity that most of you forgot. If you guys are tutoring in the Resource Center, you haven't forgotten it because it shows up all the time. And all of you in engineering are going to see this thing all the time. Sine of twice x is equal to 2 sine x cos x. That kind of thing shows up all the time, and you see that sitting right here in front of us. And so that's just the sine of twice theta. And so you oftentimes see the range written for a projectile in this form. You can look in a trigonometry book and see that problem for sure in almost every trig book that's ever been written. And this is the theory on where it came from. Okay. So when you're first doing these problems then in rectangular coordinates, do a couple of them starting with the differential equations. Okay? Don't just grab this kind of a thing, okay, or this or that. Try to work at least a couple problems out, a few problems out, to make sure you really cement this development into your head. It's really important. Okay. All right. So that's the theory. That's an example. I think what would be good to do is to go ahead and go on to normal tangential. And notice I haven't done anything with numbers yet. Okay. We'll be doing a lot of stuff where we actually do numbers. And I actually think, you know, let me go ahead. We've got the time. Let me go ahead and do one that's got some numbers in it. Not necessarily a projectile like this, but something else. So over here now in the section under rectangular coordinates, earlier today I was looking at this particular problem. I can zoom in on it. This one right up here, number 67. And while you're maybe jotting some notes down about that, I'm going to erase this hard to erase black stuff up here. If you can see my little handwritten notes there, graph with a calculator in parametric mode. If you're familiar with that, actually go ahead and crank the math out and see if you can answer that question quickly before I even get to it. Give me a holler if you've got an answer for anything there. I think you're supposed to do it at 2 seconds and 3 seconds. Okay, I hope that you folks realize that you could just crank this problem out very, very easily, right? Just by cranking derivatives on those time-dependent functions. And so, if you were just going to go through and answer this particular question, you got a position vector given in meters and time in seconds. In terms of time, you're just going to, find the angle between the two. That makes it a little more exciting. Good. I like that. Okay, good. That makes it better.